Orthogonalization. Orthogonalization is a method that takes advantage of orthogonality for least squares approximation. It is important to stress that this discussion on orthogonalization requires understanding on principles of least squares approximation. These principles have been discussed under trend analysis. We have for references the book of Meissel, who was an Austrian geodesist, written in 1982, the PhD thesis by Cosare in 2007 from our department, the book by Kreisig in 1971, and notes from Professor Peter Vanecek back in 1992. What is orthogonalization? Orthogonalization is a procedure used to find a set of orthogonal vectors that create a particular subspace. In other words, a set of orthogonal vectors that create a coordinate system. The resulting vectors are orthogonal to each other. In other words, they preserve the inner product property in an Euclidean space. They have the same linear span as the original vector set. There are a few approaches for orthogonalization. There is the Gram-Schmidt process, which uses projection. There is the Householder transformation that uses reflection, and the Givens rotation. In this video lecture, we're going to discuss the Gram-Schmidt process. Why orthogonality is important? Consider these two vectors. They are actually row vectors, and they are row of the Vandermonde matrix. They are orthogonal on the definition set with a weight matrix P if and only if their scalar product equal to 0. Now let's consider a transpose of a Vandermonde matrix. We can say that its individual vectors or row vectors will be orthogonal on the same definition set D with the weight matrix P if and only if they satisfy the condition that their scalar product equals to 0. Every time that two row vectors satisfy this condition, they are orthogonal, and otherwise when a row vector multiply itself, what we have is essentially its square distance or the square norm. We can say the quadratic norm. An orthogonal system is useful because the Gram matrix is diagonal. Again, from least squares approximation, we know that the Gram matrix plays a similar role of the normal matrix in a least squares parametric adjustment. And from the Gram matrix, from the inverse of the Gram matrix, we can compute the covariance matrix of the coefficients. And how do we compute the coefficients? The coefficients, the I coefficients for U unknown coefficients, they are going to be the product of each individual row of the Vandermonde matrix by the observation vector divided by the quadratic norm. This constitutes a system of U equations which will then degenerate or boil down to a set of U independent equations. An orthogonal system is the best base in the sense of best coordinate system. If you go back to the equation for lambda hat, we can write here explicitly in an attempt to make it clear what it really represents. So in case we have, say, two coefficients, the first coefficient is going to be computed by the product of the row vector psi1 and the observations, which is a column vector, divided by the quadratic form. So, and explicitly we have what it represents in here. For the second coefficient, we have the same, and for every coefficient, we're going to have a same procedure. It is always the product of each individual row of the Vandermonde matrix by the full set of observations divided by the quadratic norm. The goal of orthogonalization is to obtain an array composed of orthogonal base functions. Orthogonalization is obtained by building an operator T that transforms the original elements of the van der Monde matrix into its orthogonal part. So that's the whole process of orthogonalization. And then let's look at what the contents of this product. We have here the product of, we have the original base functions, capital Phi, multiplied by T. This is the orthogonality operator, and that results into phi star, which contains the orthogonalized base functions. The Gram-Schmidt orthogonalization can be accomplished by, for every ith observation L, by writing down a generalized polynomial in which we have the ith element, phi star, is going to be the summation from 1 to I minus 1, where I corresponds to the number of unknowns, of this coefficient alpha sub ij multiplied the base function phi star j. Star represents orthogonalized base function plus the original base function phi sub I. If we start to write the equation, the generalized polynomial, for each individual element, so for the first element, phi star sub I equals to 5 sub I, then 5 star 2 is going to be equal to alpha 2 1 multiplying phi star 1 plus phi 2. And of course, we know from the previous expression that phi star 1 equals to phi 1, so we can actually replace here. And then we have phi star 3, which again, it follows generalized polynomial, which satisfies the Gram-Schmidt orthogonalization. 5 3 star equals to alpha 3 1 phi star 1 plus alpha 3 2 phi star 2 plus alpha 3, and so on and so forth. We can actually write down now these set of equations in matrix form, and this is what we have. For example, for 3 observation equations, what we have on the left-hand side, we have the orthogonalized van der Monde matrix. We can see the row vectors of the van der Monde matrix. Again, these elements, the phi 1 star, phi 1 star, phi 1 star, they are the same element, the same thing for phi 2 and same thing for phi 3. They represent the same quantity. And then we have the T matrix multiply the original van der Monde matrix. We can rewrite these expressions in vector form, and then we just have the final equation phi star equals to T times 5. How do we get these coefficients of alpha sub ij? They have this general form. Alpha sub I will be equal to the inner product of a original base function I and a orthogonalized base function j divided by the quadratic norm of the base function sub j. Let's prove it. The first one, we know that phi star 1 equals to phi 1. So for the second one, this is the result of the Gram-Schmidt generalization. And if we multiply both sides by phi star 1, we obtain this equation. But we know that inner product of these vectors, for them to be orthogonal, have to be equal to 0. And we also know that the product of phi 1 star times phi 1 star is basically the quadratic norm for phi 1. So here is what we have now, replacing all elements. And now what we have to do is evaluate the value of coefficient alpha 2 1, which is then given by the product of row vector phi 2 phi 1 star divided by quadratic norm of phi 1 star. The proof for coefficient 3,1 follows likewise. We start from the expression from the Gram-Schmidt generalization. We again multiply by phi 1 star, and we will have inner products that have to be equal to 0 to satisfy the condition of orthogonality. And we also have the cross product of phi star 1 by itself, which is the quadratic norm. And then we finally have the equation for the coefficient 3,1. Likewise, coefficient 3,2, we have to multiply the equation at the top by phi star 2. We follow the same development, and we have now these equations. So we can then generalize by saying that the coefficient alpha sub ij equals to minus the inner product of phi I and phi star j divided by the quadratic norm of phi star j. What if you want to do a de-orthogonalization? De-orthogonalization now would have to use a matrix T star that would transform from the orthogonal space to the original space. How do we perform least squares regression through orthogonalization? To begin with, we have to select the base functions and also the weight matrix. Then we perform the orthogonalization, which means we will generate a orthogonal van der Monde matrix, and we will use these orthogonal van der Monde matrix to estimate the orthogonal coefficients, lambda star. After done that, we will de-orthogonalize the orthogonalized estimated coefficients, and these will be done, and we can show here the development. The final equation that we are going to use is going to be orthogonalized coefficients lambda hat star will be multiplied by the transpose of matrix T, and that will result in the coefficients, the estimated coefficients in the original space. That will give us then the final solution. The trend is going to be the generalized polynomial, as we discussed when we talked about approximation, least squares approximation, and we can use these for predictions in the same way as we used before.